Velocity, or motion, how fast you're moving, is a very familiar concept to most people, especially those of us who've driven in cars, which is pretty much all of us here in the United States. Driving 5 miles an hour is relatively slow. Driving 55 miles per hour is relatively fast, especially if you're driving in the side streets of some city. Velocity holds a very special place in the history and development of physics, especially in Einstein's special theory of relativity, where the velocity of location of an observer is very important in determining distances and time. Time and distance are relative to the location of an observer. Now, I proposed a theory several years ago that velocity also holds a very special place in scale, the size of the observer. And time and distance also are relative to the scale or size of the observer. Now, I'm going to use a young lady, Scarlett, in 3 situations to depict what I mean by this relative scale. So the first scale we'll say is a normal scale. Imagine Scarlett. Scarlett is a young woman who's healthy and strong. She's 5 foot 3 inches tall, and she likes to run. And she runs often, and she knows how fast she runs. On average, she runs a mile at 5 miles per hour in 12 minutes. She runs about in a straight line, stops for a moment, turns back, and runs back another mile. Now, she's very familiar with this process. She's done it often. She doesn't even need a watch anymore. She knows how fast she's moving by how fast the objects are moving past her, and how she feels, how her body feels, and how she moves. She physically feels a certain way, and she is aware of the passage of time, and she knows approximately when she's run a mile and when about 12 minutes are up. Now let's consider another scale, Tiny Scarlett. Tiny Scarlett will be 1,000 times smaller than our normal Scarlett, who was 5 foot 3 inches. Tiny Scarlett is 1/16 of an inch tall. That's very small, tiny, compared to normal Scarlett. Now, this Scarlett is the same Scarlett in all aspects. She likes to run, she's vigorous, she's healthy, she runs all the time. She knows when she's run a mile. She runs a mile in about 5 miles per hour. It takes her about 12 minutes to run a mile. She runs roughly in a straight line, stops, turns around, and runs back. She knows how far she's run. Although she has a watch, she knows the distance. She doesn't really need it, just like our normal Scarlett. Now, the interesting thing happens when normal Scarlett looks down one day on the floor and sees the little itty bitty tiny Scarlett down there, 1/16 of an inch. And she notices she's moving in a straight line about 5 feet 3 inches. Stops, turns around, and then she runs back in a straight line. Now, it takes her less than 1 second to run that straight line relative to normal size Scarlett. In fact, 0.72 seconds. And she's only running 5 feet 3 inches. So they disagree on the distance, and they disagree on how long it took the time, yet both completely agree that it's 5 miles per hour. And there is scale relativity. Now let's consider another scale, Giant Scarlett. Giant Scarlett is 1,000 times taller than normal Scarlett. She's 5,280 feet tall. That's 1 mile. Giant Scarlett likes to run. She's similar in every way to the other 2 Scarletts we've mentioned. She is healthy. She runs a mile. She runs in a straight line. She runs about 5 miles per hour. It takes her 12 minutes to run that mile. She stops, turns around, runs back. Of course, it gets very interesting again when normal Scarlett is looking up at Giant Scarlett. Of course, she sees her. She's a mile high. She sees her take 1 stride of her run, and it takes about 7 minutes. And if she uses Google Images or a telescope and she can track how far she's run, she thinks she's run 1,000 miles for 200 hours. That's 8 1/3 days, and then turns around and runs back. They both agree that Giant Scarlett was running at 5 miles per hour. Giant Scarlett thinks she's run a mile in 12 minutes. Normal Scarlett at her height thinks she runs a mile in 12 minutes. Tiny Scarlett at her height thinks she runs a mile in 12 minutes. It's when these scales are viewing and measuring the other scales, they all agree velocity doesn't change. It's invariant. But the distance and the time is relative to the size of the observer. Now, Giant Scarlett can also look all the way down if she uses a microscope and see tiny Scarlett. Tiny Scarlett is 1,000,000 times smaller than giant Scarlett. Tiny Scarlett runs a mile, but this time it's in 1,000th of a second. Less than that, less than a millisecond. And moving a very tiny distance. So as the size gap increases between the scales, so does the difference in observed heights and distances. There's also several other important physical observables that change as well with scale, and I'll mention those briefly in a moment. I like to consider this a real fundamental aspect of our reality, this essence of time to the size of the observer. It's relative to the scale of the observer. Now, a common household fly is about a half a centimeter tall and roughly 322 times smaller than our normal sized Scarlett. That fly, if it has a conscious awareness at all of its existence of time, we think a housefly lives relative to us for about 3 weeks. This would be 2 to 3 years in the consciousness of the perception of time of the fly. Now, when a fly flies past Scarlett really quickly from the left to the right in about a half a second, or any human at this scale, we see the fly, goes by rapidly, maybe 15 miles an hour, maybe 5 miles an hour, but it seems fairly quick, taking a half a second. To the fly, this is 2 to 3 minutes long. So you can imagine from the fly's conscious perception, the giant human it's flying by is moving slowly. And the fly has a lot of time if you imagine an airplane from way in the sky flying over a city, slowly passing a building. Now consider even smaller bugs like an ant. That might even be 1,000 times. Its conscious perception, its mind, might be 1,000 times smaller than our normal scale Scarlett. When you step on a bug in 1/10 of a second and kill it, maybe stop and think that that poor bug sees that shoe coming down and crushing it. It takes maybe 5 minutes to be completely smashed. Now don't go and run out and kill a bunch of bugs. Maybe you should spare them. Now one more concept. Mass, charge, density. Other physical parameters do not scale at the same rate as length or volume. And that's why physicists or engineers realize you cannot just scale a human being, a normal size human being like Scarlett, to giant scale. It's just not possible. The structure would collapse. However, mass does not scale at the same rate as volume, nor does the charge of the atoms, the electromagnetic forces that hold together the human being. And that I'm going to talk about at another time. Just realize it can scale, and it does scale. Thank you. This Scalativity episode was produced by Z23 Studios. Make sure you subscribe to our Scalativity channel so you don't miss an episode. Please go to scalativity.com to read the 5 initial fractal physics articles published online in the Fundamental Journal of Modern Physics. Scalativity.com also includes 3 groundbreaking, amazing articles available nowhere else. Until the next Scalativity episode, this is Leonard Malinowski, inviting you to help me advance physics.